Alrighty, hello to all you folks online. My name is Zach. I'm a Math 1553 TA, and this is my final exam review. So this exam obviously encompasses everything. It's weighted a little bit heavier towards the end of the class, not because the first stuff is less important, but because you need all of the first two exams to even be able to think about the last couple of exams worth of content, okay? So I'm just going to start taking questions. I'm not going to go over any kind of big concepts. I'll take them as you ask them. I will answer them. It can be as broad as what is the span versus solution set, or as precise as do this question on this exam from this year, whatever. Okay. So questions? Yes. Orthogonality. Sure. Move this up a little bit. Orthogonality. Okay, so what is orthogonality? It is essentially just perpendicular in a higher dimension, okay? So for example, if we have a simple graph and we have a line, okay? A line that is orthogonal is just a line that sticks straight off with a 90-degree angle, okay? If we're in 3D instead, okay? We have X, we have Y, we have Z, right? What this means is if I have some, that's not straight. Oh, Jesus Christ. If I have some line in 3D, okay, pretend that's like sticking out of the page, and I'm looking for something that is orthogonal to this, what this would look like is a line that sticks straight off this way, or a line that sticks straight off this way, or a line that sticks straight off. So what I mean by that is if this is my line going like this, okay, this line is orthogonal to it, this line is orthogonal to it, this line is orthogonal to it, this line is orthogonal to it. Does that make sense? There's some kind of, it's all the space around that that sticks straight off of that line. So in 3 dimensions, how much space is orthogonal to a line? 2, a plane, right? We can make a whole plane out of the stuff that is orthogonal to this, right? So another little tidbit that can help you out with that is the dimension of the orthogonal space plus the dimension of the original space is always the total space, okay? So we have a plane and a line, 2 dimension, 1 dimension, we're in 3D. That makes sense, okay? So that's kind of how it breaks down like that in an overarching concept. Now, something that they might ask is, given a matrix A, how do you find a basis for the orthogonal space? And in your notes, in I believe the 6.2 chapter of the book, it gives a nice little formula. The null space of A transpose is equal to the column space of A perp, okay? This little upside down P means perp or orthogonal. It's just the orthogonal space to that, okay? So if we're given a matrix A and we're trying to find the orthogonal space, we find the column space of, or this isn't something that's just easy to compute, right? But to find the null space of A transpose, that is a much easier thing that we know how to use. We've been doing that for the last 2 exams, right? 3 exams, okay? Questions on how to like find an orthogonal space given a matrix or given a couple lines? Does that make sense? Okay. And there's a few other formulas that go with this, okay? There's actually 4 formulas that are all identical. And all they are is switching where the T is and switching where the orthogonal bit is, okay? You can just memorize the formulas if that doesn't make too much sense to you. But essentially, there has to be 1 orthogonal bit in a red circle, and there has to be 1 transpose in a blue circle. You can't have both. You can't have neither, all right? So this creates other formulas like null of A transpose perp is equal to the column space of A. Or the null space of A is equal to the column space of A transpose perp, or the null space of A perp is equal to the column space of A transpose. Okay, these are all the exact same formula. All right, if they ask you to find any one of these, you should be able to do it pretty easily. Okay, well, not, you know, true false answer easily, but know how to do it easily. Okay. This is something I like to ask. It's usually like the final is usually 10 or 11 questions. Second to last question is usually some kind of orthogonal bit. And the last one is always the least squares. You'll see that on any practice exam. The last question is the least squares. Yeah, so that's how you find it. And what they may also ask is, given something, the distance from a vector to another line is the orthogonal component, okay? So what I mean by that is orthogonality is most important, okay? Because it talks about projections, okay? And the way we kind of relate that is if I am in R2 And this is my space A, I'll call it, all right? My space W, it's all the same thing, all right? If I'm doing this line, okay, then what my projection is, okay, because projections and orthogonality go hand in hand, all right? The projection is the bit on this line that goes as close as we can to here, okay? It's the part that's on this line that is under the vector, all right? If it's tilted, it's a little bit more complicated to think about, but the way I like to picture it is if there is a giant flashlight above it, okay, and it's shining straight down, all right? What we're left with is this part right here, which is the projection of, we'll call this y. Projection of y onto A is how that can be written, okay? So we can also break this vector up into a second part. And what that second part is this part that's sticking straight up, okay? This part that's sticking straight up, we'll notice that it's orthogonal to A, all right? So we call this the orthogonal component of y, okay, which is often written y per, just like that, all right? And one little sidebar with that is y is always equal to the projection of y onto A plus y per, okay? It's just this vector plus this vector gives me the original vector, right? Yeah, so that's what orthogonality is in a nutshell. It's the part that sticks straight off when we project, or it's just anything sticking out of our space, okay? Any questions on that? Okay. One other note is the distance between your vector and that line is the magnitude of this y perp. You see, that's obviously the distance from right here up, okay? So how do you find a magnitude of a vector? It's always just 1 over the square root of each entry. So we'll call it a squared plus b squared plus c squared plus dot, dot, dot. Or sorry, the magnitude is just like this, okay? This is the magnitude of some vector with entries a, b, c, d, etc. Okay. So to find the distance from a line to a space, okay? So in this case, distance from y to a, or a to y, it's the same thing, is the magnitude of y perp. Okay. Okay. I think that covers the general idea of orthogonality. Any other questions on this? Yeah. Yeah, that's the distance from from A to Y. Okay. The distance of just this vector here. Does that make sense? Okay. Because it's the part that's essentially sticking up. Because we have this much in the space itself, and there's only this much difference between them. Okay. So it's just the magnitude of y perp that we have to consider. Okay. It's the distance from the tip of it to the closest point in A. And another fun little definition is the projection is always the closest point to that vector. Okay. So this projection here is the closest point on A to Y, right? There's not a point closer that exists. For those of you that are going to take multivariable calculus, you'll see that a fair amount. Is like what the class opens with, actually. So, yeah. Other questions? Not necessarily on this, on anything. Homework questions or exam questions or anything? Yeah. Sure, I can go over a best fit problem. Yeah, they usually, I'm just going to do one from a practice exam. So let me find one from Jankowski's website real quick. And I promise, if you have a question to ask that you feel like is a stupid question, there's probably half a dozen people in this room at least that have that same question, okay? Practice final exam. So let's go to problem 10. All righty. Yeah. Yeah, that's what this one is. Kind of. Oh, that is not this. And no. You do need that for the final, though, so I am sorry. Why? Because you know rotation matrices. Technically, right? You need to know that, and you need to know the quadratic formula. Those you're expected to know, you're Georgia Tech students, and unfortunately, that's what it is. Come on. Okay. Don't need that. That's not the right file. Alrighty. So least squares and projections are actually go hand in hand. They're the same kind of problem, but one stops a little shorter than the other. Okay. Least squares is a kind of statistical analysis that uses linear algebra to get a line of best fit. Okay. So there's a method to always follow with these. All right. And that is always, there's a few steps for least squares. Okay. Step 1 is find A and B in AX equals B. Okay. Always step 1. All right. Step 2 is find A transpose A and A transpose B. Step 3, solve A transpose A augmented with A transpose B. Okay, and what this does is the solution. Solution is equal to what I'll call x tilde. All right, and what this is, that's not any proper term. It's just it doesn't really have a formal name, so it's just what I usually call it. Okay. And with this, what x tilde is the input that gets us closest. That's not how you spell that. Gets us closest to B for A times X. Okay. So this is all you need for a least squares problem, but there's one more step in case they do ask it. And it is a foolproof way to always find the projection. Okay. A times x tilde is equal to the projection of B onto W, where W and A are just the same space. Bless you. A is usually the matrix that spans W, but this is just how it's typically written. Okay. So it's pretty computationally straightforward. Find a couple matrices, multiply them, row reduce, so on and so forth. Okay. When in doubt for this exam in this class, I said it before, but I'll say it again. Put in a matrix and row reduce. You'll probably get about halfway there at least. Okay. So for this question, what we have is we have to first arrange it so that we have a least squares for y equals mx plus b. So we're solving for m and we're solving for b. All right. So when we plug in these points, what you should always do is you should try and make an a and make a b. All right. So we're going to have, when we plug in the first point, 11 equals m times 0 plus b. For the second one, we have 2 equals m times 3 plus b. And for the third point, we have 5 equals m times 6 plus b. Okay. So from here, we can rewrite this as 11 to 5 equals 0, 3, 6, 1, 1, 1 times m b, right? This is how we typically write our equations. I can reorder this as 0, 1, 3, 1, 6, 1, augmented with what I'll call the x vector equals 11 to 5. Okay. So this is your a times x equals b. If you have questions at any point of how I got something, or if anything does not make sense, please ask it, interrupt me, say something. All right. So from here, the process says that next we have to find A transpose A and A transpose B. So let's find A transpose A first. 0, 3, 6, 1, 1, 1 times 0, 3, 6, 1, 1, 1. Which what I do is I build my little bridges to show which rows and columns are connected. And that gives me my product is 9 plus 36, 9, 9, 3. Okay. So A transpose A is equal to 45, 9, 9, 3. And next we have to make sure we do A transpose B as well. So 0, 3, 6, 1, 1, 1. And B was 11, 2, 5. Okay. So I'll do some green. So this gives me 6 plus 30. 11 plus 2 plus 5 is 18. So that gives me A transpose B equals 38, 18. Okay. So that's step 2. Very nice. Step 3, solve A transpose A augmented with A transpose B. So do those 2 dimensions work for this problem? Can we augment them? Does that make sense? Yeah. Oh, you were so right. Math is hard. One of the things I do like about how this class is taught is the numbers don't count as much as the method. So if you miss a number, it's not going to give you a 0 for the question. As long as you generally know what you're doing, you'll do pretty okay. All right. It's just a rule of thumb at Georgia Tech, which is how most professors grade, and the ones that don't suck. So this is 45, 9, 9, 3 augmented with 36, 18. This makes sense to augment because we have a 2 by 2 augmented with 2 by 1. All right. And now I'm not going to make you watch me try and row reduce this extremely painfully. So I'm going to do it in MATLAB real quick. I know it's not that hard, but I don't want to do it. It's what, 1 minus 1? No. Whatever. My brain is absolutely fried today. I spent all day just trying to get my research stuff to work, but it didn't. So, but such is life. So this gives me 1, 1, 0, negative 1, augmented with, nope. That's not how that's written. 0, 1. Okay. So what this means is my x tilde is equal to negative 1, 9, which, if you go back a little bit, that was MB is how we wrote that. So M is equal to, yeah. A 0 in where? Never. Okay. Yeah. If you were about to correct MATLAB, that'd be a big deal. So M equals negative 1, B equals 9. So this gives me the equation in the original context of y equals negative 1x plus 9. And that's how we do that. Any questions on this? Yeah. Yeah, sorry. It's just a lot, and I don't really know the best way to orient this. So is this good? Okay. Any questions on least square stuff? Yeah. Yeah. So usually what we do is I put all my numbers that are alone on one side of the equation, because not every time it'll be y equals mx plus b. So you need to get all your solo numbers on one side and all of your things that are attached to a variable on the other. So like here, we have our numbers on one side themselves, and this is my M column, this is my B column. Okay. So I just order it from there and call it M and B. Okay, does that make sense? Yeah, this is my X vector, if you'll call it that. It just means this is the M column and this is the B column. Okay. Because if you want to multiply those matrices out, you'll get the original equations we had. Okay, yeah. Yeah. I multiplied A transpose times A transpose times A, and A transpose times B. Okay, and those were from our original setup of the equation, which is from here. Okay. This is just about the hardest stuff we learn in this class. It is formulaic, but the concepts are pretty difficult. Yeah, please ask questions if you have them. Yeah. When we're talking about lowercase b, we're talking about the equation ax equals b. Okay. We're talking about uppercase b, we're talking about the variable b that they named. Okay. You don't have to call them m and b if you don't want to. You could solve this whole thing by calling them smiley face and frowny face, if that's easier, or a triangle and star, or whatever you want. You know, these are just placeholders for whatever two things we're solving for. Okay. And then the original ax equals b is what we kind of work with for the least squares. Okay. So getting to here is understanding how the problem is set up, and then going from there is how you actually get a solution to a least squares problem. Okay. Yeah.
This capital B when they use it as a projection matrix.
Capital B when they use it as a projection matrix. Do you have a question that's from particularly? Okay. Because projection matrices are a little bit more broad than that, but there's only one case where you have to find a specific projection matrix, actually, and you need to know it. So any other questions on least squares before I go forward? Yeah. Yes. So what I can say is what we're doing here is we're getting these, and without going too far into the theory of why we use transposes, this gets us our projection. This minimizes our projections from each of the points. So the projection is as small, the orthogonal component of each point is as small as possible. Does that make sense? Because the whole goal of least squares is to get a line. Like here we have 0, 11, 3, 2, and 6, 5, right? So what we're looking for, oh shit. What we're looking for is some line, right, that minimizes each of these distances. So it's minimizing the orthogonal distance is what a least squares is doing, right? You're trying to get these red lines for each of them to be as small as possible, which isn't always possible. And in this case, you can see that there's no one line that can fit through all these points, one straight line. Okay, so that's how orthogonal stuff relates to least squares, all right? Yeah.
It's number 2 on the video worksheet.
Wonderful. Okay. 6.5 worksheet. Number 2, question A. I really asked because B isn't like the terminology that's always used. So like some things have one particular thing that is always used as like that letter, but projections don't really have one. Give this a second. Why would anything work as quickly as I need it to? What the shit? All right. So projections and orthogonality are actually the same thing, right? Because talking about orthogonality is talking about the stuff that gets squished when we do a projection, right? So standard matrix B for a projection W, this is the only like general kind of projection matrix you're going to need to know for the final, all right? There are ways to construct another one, but it is a much larger headache, okay? So, oh, come on, why isn't this going down? All right. So to construct a matrix for a projection, all right, there's a method we've already learned that can do this, but it's computationally heavy, all right? Is a projection diagonalizable? Yes, yes. Projections are by definition always diagonalizable. They're not invertible, but they're diagonalizable, all right? What are the eigenvalues of a projection? 1 and 0, right? So what we can do is we can rewrite this as a CDC inverse, right? This is one thing we can do to get the standard matrix B, all right? Where C is, we'll get to that in a second, and D, how many things are we projecting onto? What's the dimension of the thing we're projecting onto? 1, right? So we're projecting onto one line, so we have one eigenvalue of 1 and 2 eigenvalues of 0. So the first column of C is 1, 1, negative 1. And you can get these other two columns by doing the null space of A transpose, which is equal to a basis for the column space of A per. This is hard and it sucks, and you don't want to do this on a final. Okay? You can. That is fine. Don't. You don't have to. You don't need to. All right? But this is a method we've already learned to do this. But there's a nice little shortcut for this. And what it is a flat rule that if we are projecting onto a line, there is a simple formula to use. And that formula is 1 over the magnitude of u squared times u transpose. All right? This is also written as 1 over u dot u transpose. Okay, these are the same thing. All right? So in this case, what is my u? Yeah, it's just the vector I was given, right? So we can rewrite this as, huh? No, that's for stochastic matrices. That's percentages. For geometric space, we use a geometrical mean of the points within. We use the Pythagorean theorem for space distance. Okay. So when it's squared, however, we can also use a dot product. So that's 1 squared plus 1 squared plus negative 1 squared over 1, 1, 1, negative 1 times 1, 1, negative 1. Okay. So when we work this out, we obviously get 1 over 3 times the matrix. 1, 1, negative 1, 1, 1, negative 1, negative 1, negative 1, 1. And this is a fine way to leave your answer. All right. There's no particular reason you need to put the 1/3 in there. This makes the matrix look a little uglier. All right, but clearly this is a much faster process than finding a C and a D and then finding the inverse of a 3×3 and then multiplying 3 3×3 matrices together. Yeah. Yes. If it is any. So a couple semesters ago, I told my students that they would not ask for the determinant of a 3×3 or eigenvalues of a 3×3, and they did. So I'm cautious to say it won't happen, but it would be evil if they did that. If it was anything greater, okay? Because then you have to do CDC inverse, and there's not a simple formula. This is the case that they want you to know because this formula is helpful for a projection onto a line. So this is the only formula you need to know for a projection. Yes. That is a much more complex question than you might realize. I would suggest Googling it. Probably a projection? Yeah. No, probably not. That's the question she asked as well. Projection onto something more than a line would constitute like a CDC inverse projection, general matrix. Okay, that would be to find the matrix that's projecting. Something they could ask was find a basis for the line that is. But to find a general transformation matrix for that is more complicated. Yeah. This is the only use. Okay. To find the projection of V onto this, if I'm not mistaken, we just let me double check this real quick because this is one thing that I don't want to say incorrectly. Any other? Yeah. You can do that as well, but that's you'd have to have a B. So you'd have to have a single vector you're trying to project onto it. So that when we do that, we have to be given numbers we're trying to get close to, right? Here, we're not given numbers we're trying to get close to. We're just trying to find a general matrix that projects. Okay. We just need an A. So we can't just compose an A because we only have one vector though, right? And well, if we try to do it like that, right, we'll have A transpose A. Okay, and we can do this. This is what this matrix was. But what is A transpose B? Yes, that is a fine way to do that as well. I forgot. That is the equation I was trying to pull up because I didn't want to say it incorrectly. Let me find where that is really quick. Orthogonal projection. This is probably the worst formula you will see for this. Here we go. Yes, if you're right, if you're given a projection for something that's bigger, all right, I find the CDC inverse method to be easier, which is horrible, but something you can always do to find a general projection matrix is A times A transpose A inverse times A transpose. This will give you some B projection matrix. Okay. It sucks. This is probably the hardest formula you have to remember. Just to remember it, I think is fine. If they ask you something about this, it should be relatively simple. Okay, you're not going to be doing 5 by 5 inverses on the final. Okay, the final is meant to take maybe half time if you mostly know what you're doing. Yeah, and one other little sidebar to note, something you can always do to find a projection onto a line of a single vector is you can find this matrix and just multiply it by whatever that vector is. Or using some fun little trick math, we can rewrite this as u dot x over u dot u times u. Okay. Let me rewrite this as v to keep it consistent. Okay. These are just the few formulas that we use about projection stuff. All right. This is to compose a general matrix. Okay. For anything greater than a line or a line in general, if you want to do it that way. For projecting onto just a line, 1 over u dot u, u transpose. If you're looking for the projection onto a single line of a vector, it's this, or you can find the matrix and then multiply it. Okay, there are multiple methods to do most of these things. Okay. Any other questions about this? Yeah. How do you know what? It'll be very clearly stated. Yeah, like this one states, projection on a W such that the span is this single line. So we're projecting onto a line. Okay. Any projection onto a one-dimensional space is that. Okay.
In the version, it's required you to do the same formula over and over again.
To fill up the vector. Do you know? I'm not sure what you mean.
Hold on a minute. I'll pull it up right now.
Okay.
It's hard to explain.
Okay. Does anyone else have any other questions on this? Yeah. Yeah. Sure. Did you have a question on this? If you do, then you have to compose a CDC inverse. If it's bigger, or you can kind of do it intuitively with like unit vectors, right? Because that's how we did it for like the second exam. Okay. Yeah, does that answer your question? Cool.
Is that like right above that? So is that if you were trying to find the orthogonal projection on?
Yeah, this is equal to the projection of V onto U.
Okay.
Yes. Yeah, did you find it?
Yeah, basically, I know we already went over this in class. How do you find the difference from x to the distance from the vector x to w is the length of xw transpose. So you find xw transpose xw by using
So are you asking how do you find the distance from x to u?
just vector x is equal to xw plus xw.
Oh, this equation here.
xw xw the
X is equal to x sub w plus xw perp.
yes
This equation?
yes
This is if, like for this line, for u, all right? We'll call this u, all right? This is the span of u. All right. Magnitude of xw is the projection of x onto w. Okay. So the way we find this is by using one of these equations here. Okay. This one, if we're just projecting onto a line where v is x, or you can find the general matrix, multiply by x. Okay. Or you can multiply this by x and get it that way as well. These are all the same formula when you boil it down, which is horrible, but you have to know which one is the quickest one to use. Okay. And then from here, if we know, for example, that if we know x is, for example, 1, 1, 1, and we know the projection of x is 1, 1, 0, then we know that xw perp, not transpose, perp, we know that this has to be equal to 0, 0, 1, right? So then the magnitude of this would be the distance from x to u. Okay. Does that make sense? Okay. Problem 2, midterm 2, true or false, right? Is there a particular midterm you had? Okay. I'll just pull up the one from this year, if that's okay. Where did his website go? Oh, he just has midterm solutions. Okay. All right. So these are true or false from the second exam. All right. So these are the answers because that's all Dr. Jankowski has posted. So obviously the answer is a little bit more apparent than it usually is. But we'll start at the top. Suppose v1, v2, v3 are linearly dependent in R4, then v1 must be a combination of v1, v2, v3. If they're dependent, what does that mean that v1, v2, v3 has? If they're a dependent set of vectors, what do they have in their matrix? Yeah. Yes, one of them is a multiple of the other two. What does that mean in terms of pivots? There is one missing. We have a free variable, okay? So this has at least one free variable. One of the most complicated parts about trying to explain true or false is each of these questions can probably be explained half a dozen ways. So if it doesn't make sense to you, ask it in a different way, or maybe say, what does this mean in the context of this, or anything like that, and we can steer this in a different direction so I can try to explain it that way. But so this means that there has to be at least one free variable in v1, v2, or v3, all right? Or some combination of v1, v2, v3, or multiples of each other, okay? One of them is in the span of some combination of the other two, all right? So does that mean that v1 is a linear combination? Does that mean v1 has to have a free variable if we know the whole set of them has at least one? No, it doesn't have to, okay? An example matrix of this would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, okay? In this case, v1 is not a linear combination of 2 or 3, because separate from these two, this has a pivot and this has a free variable. So this whole set has a free variable, so they're dependent vectors, but v1 is itself, yeah, cool. So the next one says if A is 3 by 8, so we always draw this out. 3 by 8, then the dimension of the null space must be greater than the dimension of the column space. What is my dimension of null space equal to always?
The maximum of the null space. No, the dimension of the null space is equal to the number of variables.
It is equal to the number of free variables. Very nice. So number of free variables must be always greater. And what is the dimension of the column space? Number of pivots. Lovely. All right. So how many pivots can we have at most? 3. How many free variables must we have at least? What's the smallest number of free variables? 5. So that's kind of how we can think about this. Think of the minimum number of free variables and the maximum number of pivots to try and solve this equation. Okay. So we must always have at least 5 free variables and at least 3, at most 3 pivots. So that's the most extreme case. So obviously that's true. 5 is always greater than 3. All right. So consider the subspace of W of R. Subspace W of R4 given by the following equation. Then the dimension of W is equal to 3. Well, if we see something equal to 0, what else can we call that in terms of spaces?
Null space.
Null space, right? Equation equals 0, null space, right? Is a null space a subspace? Yes, that is why we learned subspaces in this class. Okay, null spaces and column spaces are subspaces. What is the dimension of a null space equal to? Number of free variables. If we put this in a matrix, how many free variables do I have? 2. Okay. D says, suppose we're going from R4 to R3. Then for each y, there is a vector x such that t of x equals y. So there is a vector x such that there is a y. What else is that called? Being onto. 1-to-1 would be each x has a unique y. There's no y's that have doubles. Okay. So just because it's wide, does that mean it's onto? No, we have no idea, right? There's no numbers, there's no other kind of indication. Could it be onto? Onto means a pivot in every row or column. Row, right? Onto, pivot in every row. Can this have a pivot in every row? Yes, it could, but it doesn't have to. Okay, and the last one, A is n by n, and the matrix equation A of x has at least one solution for each b. Saying something has at least one solution for each b means what? What else does it mean? 1-to-1 and onto, which is the definition of being invertible. Okay. In particular, at least one solution means it's onto, but since it's n by n, it's both. Okay. Cool. Any questions on these? Yeah. Yeah. Just think you always start in x and end with b, right? And so it's always ax equals b, right? So this is where we start, this is where we end. This is in my number of columns, this is my number of rows, okay? So it's always start, end. Okay, R4 to R3. Okay, that's how we know the dimension of that. Yeah. Sure. For true or false. There are a lot of different ways that could be asked. So one thing they could say is for some b, ax equals b is inconsistent. Okay. Can a be invertible? No, because there's some b it can't reach, which means it's not onto, which means it's not invertible. It's kind of how that can go. Yes.
That could be if every row, every column would be onto, right?
No, onto is row.
Row.
Yes. Yeah. Columns are 1-to-1. All right. Another question they could ask about something about inconsistency. If ax equals b is inconsistent, then how many pivots could this matrix have? And say that matrix is, say it's 4 by 5. Okay. If it's inconsistent for some b, how many pivots can we have at most here? 3. Why?
Because one would necessarily be a 0 row thereby.
Nope, doesn't have to be a 0 row.
That's what they.
No, it doesn't. Not in A, it means when we row reduce, we get a 0 row. Okay, it doesn't mean we start with a 0 row. Okay. For example, something that's inconsistent would be 1, 1, 1, 1 times x equals 1, 2. Okay. There's no 0 rows, but this is clearly not consistent, right? We try to row reduce, we'll find a pivot in the right-hand side of the augment bar. Saying something is inconsistent is the same thing as saying when we row reduce this, there's a pivot here. Okay? Does that kind of answer your question? Cool. Other questions? Yeah. Yes. So the way that we can kind of read this is there is a vector x so that t of x equals y for each y. Okay, so for all y's, we can get there by some x. Okay, so for all y's, we have at least one way to get there. We have at least one way to get there. We call that onto. Does that make sense? They're very tricky in this wording. Okay, but you have to really kind of get in the weeds. And most of these questions you read like this mean onto 101, when for each or for all, or something like that. Yeah.
Of that for every y there is x for 1 to 1.
That would be for each y, there exists a unique x such that t of x equals y, or y is not in the span of A. Or another way to write that would be for each y, there is a single x such that t of x equals y, or y is not in the span of A, or y is not in the range, or y exists, or ax equals y is inconsistent. Okay, does that make sense? Or for each y, ax equals y has 1 or 0 solutions. Is another way you could write that. Yeah, yeah. Or at most 1 solution is another way that that's commonly written. Sure. Why does it have enough pivots?
Because since there are 3 rows, there are 3 pivots.
Why are there 3 pivots if it's just shaped this way? Yeah, just because it's shaped this way doesn't mean we have that many pivots. Does that make sense? Yeah. Yes, this would be true if it was onto. We don't know. Yeah. So we would need more information to determine if it is onto. What this question is saying, hey, I have a 3 by 4, is it onto? Who the hell knows, right? There's no information there. It could be. It doesn't have to be, though. For example, you could fill this matrix with all zeros. Yeah. Problem 3, midterm 3. I sure can. And why did he not post the PDF? Problem 3, midterm 3. Any particular sub-question? All of them. Alrighty. Something else I will say is I know I said, like, I told my students one year that they wouldn't have you find eigenvalues of a 3 by 3. And I know y'all had to do that, but it was a triangular. So I feel like that is much different than just a thing full of numbers, which is much more complicated. So looking at problem 3. Okay, starting from the top. Let A and B be 3 by 3 matrices satisfying the following conditions. Determinant of A is 2 and determinant of B is -3. Then which of the following must be true? Okay. Problem part 1 here, never true. Well, not always true. This isn't really something you can break up. We can't break up determinants with pluses. Okay. So that one is just right off the bat not true. Okay. The second one, determinant of A transpose times B inverse is equal to -2/3. Well, we can write this as determinant of A transpose times determinant of B inverse, which is equal to the determinant of A, because determinant of A transpose is just determinant of A. Determinant of B inverse is 1 over the determinant of B. So this gives me 2 over -3, or -2/3. Okay. The determinant of a constant times A is equal to the determinant of A times -2 raised to the n, which in this case it is 3. So this gives me 2 times -8, which is -16. Okay, this is just applying determinant rules to try and solve for these numbers here. Okay, any questions on these kind of determinant rule questions? Yeah. Sure.
The value probably would
Yeah. So there's two big things that determinants determine. Okay. Determinants determine invertibility, and determinants determine if you have an eigenvalue of 0. Those are the two big things. Okay. If your determinant is 0, you are not invertible. Okay. You have been determined to have a value of 0. You are not invertible. If your determinant is 0, you are determined to have an eigenvalue of 0 as well, because the determinant is equal to the product of your eigenvalues. Okay. And if you have multiply all of your eigenvalues together and you have 0 times 0 at the end, it's all just 0. It doesn't matter what the rest are. Okay, so those are the two big things that it ties to. And you can only have a determinant for a square matrix for this class. Yeah, anything beyond that is a massive headache. So we don't do that. It also doesn't really, it's not really the same thing. But yeah, does that answer your question? Those are the two big things that determinants mean. All right. Moving on to part B here, suppose A is n by n, which is the following guarantees that lambda equals 4 is an eigenvalue. Okay, the first one guarantees that the equation has infinitely many solutions. If this has infinitely many solutions, what does that mean about the invertibility of A minus 4i?
Not invertible.
It's not invertible, right? Because this is infinitely many solutions, it's not invertible, right? So, as we just said, how can we rewrite that something's not invertible? We can say the determinant of A minus 4i is equal to 0. Okay? So this implies this. If the determinant of A minus 4i is 0, is 4 an eigenvalue?
Yes.
Yeah, that's the definition of the equation we saw, right? The second one, there is a non-zero vector in X such that X and A of X are linearly dependent. That means that we have an eigenvector. It exists. We have no idea what eigenvalue it corresponds to, though. This just means that we have some X and lambda X that exist. Okay? It doesn't tell us what that lambda is at all. If it said linearly dependent by a factor of 4, that still doesn't guarantee it technically, because it could be 1/4 going the opposite way. But if you see something like this, it's not an eigenvector. 4 is not even written here, right? So there's not really anything we can tell. The next one says there is a non-trivial solution. So there is a solution to X equals 4x. What is that the definition of?
That's literal eigenvalue.
Yes, it is. It is literally eigenvalues and eigenvectors. That's the whole definition, right? That's the motivation. AX equals lambda. AV equals lambda V, right? That's an eigenvector. And for the last one, what do we call the null space of A minus lambda I? That is a fancy name. What do we call it as a space?
The eigenvector.
Not the eigenvector, the eigenspace, right? So if the eigenspace is empty, is it an eigenvalue? No, right? There's no eigenspace, so there's no eigenvalue for that. Okay. Any other questions on eigenvalues here? Okay. Moving on to the last one. Suppose A is a 3×3 with a characteristic polynomial A minus lambda I equals lambda times lambda plus 1 squared. Which of the following statements are true? Okay, well, what are my zeros of this equation? 0 and -1, right? So what does that mean my eigenvalues are? Wow. Okay. A cannot be diagonalizable. All right. So we have 1 lambda. So how many eigenvectors do we have for lambda equals 0? We have 1 for lambda equals 0. How many do we need for lambda equals -1 to be diagonalizable, right? Do we know it has 2?
Yeah.
No, we don't. We know it has an algebraic multiplicity of 2. We don't know if it has a geometric multiplicity. For that, we would need to check the eigenspace and the dimension of that. Okay, it could be diagonalizable. Doesn't have to be. Okay, so it can be diagonalizable. Okay, it's not a must that it isn't. All right. The last one says the null space of A must be one-dimensional. What's another way to say the null space in terms of eigenvalues? The 0 eigenspace. Very nice. Okay, because the 0 eigenspace, right, is when we take the null of A minus 0I, right? Which is just the null of A. Null space is just the zero eigenspace. So, like we said before, what's my algebraic multiplicity of lambda equals 0? What's the power here? 1. So how many vectors must it have? 1. It must be one-dimensional. Any questions on this? Yeah. Why is it not diagonalizable? Well, one case that it's always diagonalizable is if you have distinct eigenvalues, right? So we would have 3 different numbers, but here we only have 2 different numbers for a 3 by 3, right? So we're not guaranteeing it's diagonalizable. We would have to check to make sure we have 2 eigenvectors for lambda equals -1. Okay, because to be diagonalizable, we need to fill C and D, right? And we know we can always fill D, 0, 1, 1, 0 is everywhere else. We know there's some eigenvector for 0. We know there must be at least one eigenvector for 1, but we don't know if there's a second. Okay, so since we can't guarantee there's a second, we don't know if it's diagonalizable. Other questions? Anything else? I know I got here late, so I'm just going to stay here for a while. So, question, yeah. Part number 1 on the practice final. Okay. Which part? Part what? F. Oh, good Lord, that's a lot of true or false. Where did that go? Oh my God, it's so little. All right. If A is 3 by 3 and the dimension of the null space is 2, then the eigenvalues must be real. Okay. If we have complex eigenvalues, what can you tell me about complex eigenvalues? They come in pairs, right? So we just said that the null space is the same thing as the 0 eigenspace, right? So how many eigenvectors do I have for lambda equals 0? 2, right? Dimension of A minus 0I, the null space of A minus 0I is 2. We have at least 2 vectors that correspond to A minus 0I. So there's only one more eigenvector left to be taken, okay? And they come in pairs, so we can't pair it with anything else, okay? So if this is a 4 by 4, it doesn't have to be true, okay? But since it's a 3 by 3, that only leaves one spot left. We can't fill just one spot with one complex number. They have to come in pairs, okay? Yeah.
I know it's true, principally, it's just hard to believe that there would be no way to make it like your.
Okay, so, oh yeah, you're good. Oh, you're good. Oh, shit, I'm sorry. All right, so one way you can think about this is if we have a dimension null space of 2, then that means we have to have the characteristic polynomial has to be lambda squared times lambda minus some number, okay? And we can't have that number just be imaginary unless we're dealing with imaginary matrices, which we are not, okay? So since we can't just plug an imaginary number here, it can't be complex, okay? Because we need a whole like square of everything, right? We need to be able to apply the quadratic formula. So we need A lambda squared plus B lambda plus C for that to be able to apply the quadratic formula and get complex roots. Okay, so this would be a 4 by 4. So you have lambda squared, lambda to the 4th is my highest power. Yeah. All right, other questions? Yeah. Problem 1 of midterm 3. Specifically D. Do you want me to go through all of them? Okay. Go away. Jeez, fucking Okay. If this is A, then 0 is an eigenvalue. Okay. If 0 is an eigenvalue, what else does that mean? Not invertible. What does that mean about my determinant? 0. Right? So what we're essentially checking here is we're checking if the determinant is 0. Okay? Because having lambda equals 0 is having a determinant of 0 is meaning it's not invertible. You can check any of these things. So you can row reduce it, and if you have a free variable, it's not invertible, you have a lambda of 0. You can find the determinant. If it's 0, then it's not invertible. It has a lambda of 0. If, when you take a minus 0I and find the null space, if the null space exists for just a, in this case, then it's not invertible. Something you'll find is when we take this, you will find that the determinant of a is equal to 0. Okay? And therefore, lambda equals 0 has to be an eigenvalue. If the determinant of this was not 0, could lambda equals 0 be an eigenvalue? No, because then the product would still be 0. That doesn't make sense, right? Yeah, that's right. Other questions? Sure. Okay. Huh? I will do it with my engineering potatoes. Okay, so one-to-one onto an invertible are 3 branches that all go together in different contexts. Okay, so I'll first talk about one-to-one. Okay, the biggest thing you need to know on how to find it is there's a pivot in each column. This is also saying you have at most one solution. Okay. Another way you can write this is the range of A is equal to the domain of A, which is saying your number of pivots equals your number of columns. Okay.
Codomain is RF, right?
I don't know M's and N's. I can never remember them. It's R to the codomain is R to the number of rows.
Yeah, RF.
Sure. So from here, the way that we can do this using our lovely engineering potatoes, okay, is I like to draw this with this is where we start, this is where we end, this is my A, okay, and what A does is we take every single one of the vectors in here, and they all reflect and spread out and go somewhere in this other space, okay? We call the space we start the domain. Ah, that's on M. We call this the codomain. And we call the space that these vectors actually take up the range. Okay, so when we plop all of these vectors into this range, okay, what being one-to-one means is it means for each place we start, it goes somewhere in this range, and it is the only starting point that gets there. Okay, there's no duplicates anywhere. All right. So for instance, like for maybe this point here, if my vector that starts here goes to that point, then there's not some other vector that started over here that goes there. There's no other vector that gets there as well, okay? You can think of this as essentially, I'm taking this and I'm just putting it in here because each point is going to its own whatever point, okay? We just kind of mush this stuff around, put it right here, okay? It's got to be, this space has to be smaller or equal to this space to be able to fully sit there. Otherwise, we're going to have things kind of squish into it. Does that make sense? So if we're taking this, there's only one way to get anywhere. We're not squishing or combining any other thing, okay? That's why the range and the domain must be the same size. I know they don't look the same size in this, but they are for it to be one-to-one, okay? Yeah.
The thing is, the range is basically the span of it.
That's the definition of a range, yeah. Okay, any questions on one-to-one? Yeah. Because I'm bad at drawing. Oh, why is it bigger? This, for example, could be a matrix that looks like this. because my codomain are my number of rows, and my domain is the place I start. So maybe this is a plane, R2, and I'm ending in R3, okay? So what this would look like is going from here, transform to here. What this would look like is I take this whole plane, okay, this whole everything, and oh, what the hell? And it becomes some plane here, okay? So essentially, I'm taking this, and I'm putting it here in this space, okay? Because there's no confusion. Like when we take a plane, and it becomes a plane, everywhere is going everywhere the same amount of ways, right? There's no way to make a plane a bigger dimension, right? It's the exact same. You're just putting it in a higher dimension. Does that make sense? It's why for one-to-one, we can have a tall matrix, because we're starting in R2 and ending in R3. But we can't have a wide matrix, because we can't have something go from, for instance, R3 to R2. We can't have a whole 3 space, all of everything, plop onto just a plane, right? With only one point going to one point, all right? There's not a way to do that. Does that make sense? Yeah, yeah. Yeah. Okay, so a wide matrix cannot be onto, not one-to-one, ever. Okay, wide, not onto, period. It can only be tall or square. Okay, if it's wide, we're done. No more thoughts about it. Okay, don't even have to consider it. Okay, so moving on to onto, this is what I'll just write over here. Okay, onto, these two things are converses. Okay, so if one-to-one has a pivot in every column, onto has what? Pivot in every row. Okay. If one-to-one has at most one solution, onto has at least one solution. If for one-to-one the range is equal to the domain, for onto range is equal to the codomain. Okay. If before my number of pivots equaled my number of columns, it now equals my number of rows. And that's how, if you remember one of them, you can kind of put the other together pretty easily. Okay, it's the same statements, but just kind of flipped. All right. From here, what this means is it means if I have, I'll zoom in here. So if I have my 2 engineering potatoes once more, okay, and I'm transforming by A, okay, I think I said it, but I always think of A as like a lens, all right? And we're shining all of these things through these lenses, and whatever happens is the transformation, okay? So for onto, what that means is all of my space is going to cover all of everything everywhere, okay? This whole space is going to be painted, all right? That's what onto means. We're going onto the whole space, all right? It paints this whole blob blue, okay? Maybe some things are getting jammed together. Maybe this is a 3-dimensional space, like a whole cube, and we're projecting onto a plane. That whole plane is going to be covered by that cube, right? Or it could be. Likewise, for one-to-one, we start at one place, we end at one place, 1-to-1. Okay, there's no 2-to-1, 4-to-1, 5-to-1, anything like that. Yeah.
So basically, for an onto matrix, it spans basically everything in Rm.
Yeah. Yeah, it covers the whole codomain. Yeah, that's how you relate it to span. Right, so for this one, we have to start in a space that's at least as big as where we're trying to end, okay? So what this means is it cannot be tall, because we cannot go from a 2 to 3 and fill the whole 3 space, right? So it can never be tall. It could be wide, and it could be square, okay? Any questions on onto or one-to-one? What do we call something if it is both onto and one-to-one? Invertible. Whoa. Yeah, that's the whole motivation. So we can get everywhere, and there's only one way to do it, so we can track our steps back. Okay. Other questions? Yeah.
This most recent midterm, it's problem.
Part D, final values of A such that the determinant is 0. That's the one. Okay. File, desktop. All right. So if we want the determinant to be 0, right? How do we solve the determinant? Well, we take a determinant. We do cofactor expansion, right? So somebody pick a row or column that seems easy to work down. Third column sounds just perfect to me, okay? Step 1 is I always draw my plus or minus matrix. Oh, that's a minus. Okay. And from here, working down this column, we get plus 0, minus 0, plus A times the determinant of 1, minus 3, 1A. From here, we take, you can also do cofactor expansion on a 2 by 2. You know it is just the formula, AD minus BC. Okay, so it gives me A plus 3 equals 0. So what are my two values of A that this is true for? 0, -3, right? This question actually tripped a lot of people up. Some people just saw that 0 was the solution, because if we put 0 in, then the whole bottom row is 0, the whole last column is 0, and then you can just know that's a solution. But to find the whole thing, you'd have to take a few more steps. Okay. Any other questions? Yeah. No, you can. It's the exact same process. Yeah, so each time you take a determinant, you redraw this. So for a 4 by 4, like we're going to start plus, minus, minus, plus, 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 minus, minus, minus. That's ugly. Minus, minus, plus, 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 minus, minus, plus, right? And then it's going to be number times 3 by 3, number times 3 by 3, number times 3 by 3. And then we draw this for our 3 by 3s. We don't carry these same plus or minuses. We redraw them. Okay, does that make sense? Cool. Any other questions? Yeah. Yes, that's correct. Alrighty, well, if there's no more questions, then I'm fine to call it here. Good luck on the final. I will see my students in section A on Tuesday at 6 o'clock. Is that correct? Lovely. Good luck. Let me know. Send me an email if you have any questions. My office hours are tomorrow. I don't have too much to do right now, so I'm fine to meet up if anyone has any questions. I'm around, and we'll be around for a lot longer. Absolutely. Y'all have a good night. Yeah. Whichever professor graded the question.